Okay, let's get started. I think after today we have said all that we need to say about shear and moment diagrams because we've been talking about them for a little while. But as I mentioned in our initial discussion of this unit on shear and moment diagrams, I do believe that the construction of a shear and moment diagram is among one of the more fundamental skills that is required of civil engineers. It's just one of those things that you just kind of need to know how to do. And so we do spend an awful lot of time on it because of its importance, both in analysis and in design. This will be our last day on it. We're going to talk about shear and moment diagrams for frames. We are also going to talk about structural analysis aids, which I think you'll kind of see the point as we get into this. I used to talk about this near the end of the semester, but because of the way we rearranged our calendars in the semester where we have another week, I thought it would be a good idea to talk about it now. Okay, so just a heads up, you have project submittal 1, which is due on Monday. Okay, I want to be crystal clear. You do not need to do any truss analysis. No method of joints or anything like that. No member selection. You know, all the calcs and stuff we did in that lecture. All I want are the 3 truss layouts. I want you to verify that IT equals 0, that it meets the project constraints. You know, a node in the middle at the bottom, or a joint in the middle at the bottom. That none of the members exceed the maximum member length. That it fits within the envelope. All that. And then I want you to choose one for final design and describe why you chose it. It could be any number of reasons. I did some research online, and that's what this is the truss shape that I went with. I think this will be most economical, fewest number of members. My Snapple fact said that this was the truss of the day. That was a joke, not a very funny one. No, but I'm giving you a little bit of flexibility. Please don't say your Snapple fact said that this is the one that you're going with.
Yeah, never mind. Yeah.
They had the little facts in the cap, so I'm probably dating myself a little bit with that reference. Okay. No class Friday for everybody. So, okay. Any questions? Everybody get the code. I have a couple of folks still haven't gotten the code. Did you get it? Okay. All right. Let's go ahead and jump right in. So our last topic of the of our foray into shear and moment diagrams is to discuss shear and moment diagrams for frames. We're still going to use the same principles, so I'm going to skip through that part pretty quickly and talk a little bit about shear and moment diagrams for frames. What changes for shear and moment diagrams for frames? Nothing, not really. But what does change is orientation. In other words, like, for example, if I'm looking at member AB, this column member in this frame, instead of drawing the shear and moment diagram left to right, I'll draw it, you know, bottom upwards, if that makes any sense. What I'll say is that, so this is definitely a little bit more graphical than maybe even for beams because you're literally following the direction of the arrows. One thing I will say that's, I think, noteworthy here is how a software program will construct shear and moment diagrams, because if you're modeling a beam or a frame or what have you, technically the software program doesn't really know what you're modeling. Like, if you're modeling a beam or a frame, the software actually treats it usually the same way, okay? So the way that a software program will construct shear and moment diagrams is it will go based on joint order. So in a software program, you don't number your joints. You don't go A, B, C, and D. The software program is going to number them. It's like joint 1, joint 2, joint 3, joint 4, etc. And the way the software program will construct the shear and moment diagrams are from lowest number joint to highest number joint. And I actually slipped the term there a little bit earlier. In finite element analysis or software-based structural analysis, we often use the term node, N-O-D-E, for joint. We use those terms interchangeably. So it will typically go from lowest number node to highest number node. So if you're modeling a beam, you typically model it from left to right, And so it'll construct the shear and moment diagram the way that we've been doing it. But I just mention that because when you're doing a frame analysis and you're looking at the frame and you go, that shear and moment diagram looks flipped, like it looks backwards, you might have drawn it in the wrong, different order. Like instead of down, up, you might have drawn it up, down, or something like that. So, but that'll become a little bit more clear as we start using mass hand a little bit later. Just to sort of illustrate how a shear and moment diagram is constructed, I want to take a look at this example. So I'm giving you a frame, and I went ahead and gave you the support reactions for this frame. I'm hoping that by now that this isn't terribly confusing, that you can compute the support reactions for the frame pretty easily. So we have a 60 kip load between A and B, and we have a 75 kip load between B and C. And they're both applying some sort of bending type action to the members. So just so you're aware, I might call member AB the column and call member BC the beam. So the beam going left to right, the column going up and down. So I went ahead and gave you the support reactions, and what I'm going to do is I'm going to construct the shear and moment diagrams for these members. And the way that I'm going to handle it is I'm going to just treat each, bless you, I'm going to treat each member separately, okay? So basically I'm going to construct the shear and moment diagram for this member and the shear and moment diagram for this member. In order to do that though, what I kind of need to do is break out my secret weapon, okay? When I draw the shear and moment diagram for member AB, I kind of need to know what's going on at point B in order to be able to complete the moment diagram, okay? So what I'm going to do is I'm going to basically cut a section. Now you can think of this two ways. You can say I'm going to cut a section like this and a section like that. So I'm going to cut a section sort of on either end, which if you have a frame that has multiple members together, it goes like this. Maybe I'll do it like this. Maybe what I'll do is I'll cut a section like right here at point B, like just to the edge, and then I'll do the same thing for the beam. And then maybe what we'll do is we'll investigate the joint equilibrium right here on the board. So let's go ahead and do that. All right. So let's look at member AB. Okay. So let's look at member AB. Okay. So member AB is going to be like this. Actually, let's draw that a little lower.
What is the vertical reaction level?
That's 30. 30 right there.
The other one?
Over here,
The other little bit above.
this is 45 and that's 75.
Okay, thank you.
Sorry about that. So here's our support here, and what I'm going to do is I'm going to draw the known quantities. We'll draw the known quantities in red. So I have a a 60 kip reaction here, and I have a 30 kip reaction right here, okay? And then in addition to that, I have a 60 kip force right there, okay? And then in terms of dimensions, I've got, this is 10 feet. This is 10 feet. Okay. All right. So let's label this. We'll label this joint A, or node A, since I threw that term out, A. And then we'll do this as B. Okay. So, all right, let's go back to basics. Okay, so in order to construct this, I broke out the secret weapon of structural engineering, which is a samurai sword or a lightsaber if you happen to be a sci-fi fan, right? Okay, so when you cut a section through an arbitrary point in a structure, you have at most 3 unknowns, right? There are at most 3 unknown forces. So I want to treat each of those independently, okay? So if I sum forces in the x direction, what is the horizontal force inside point B going to be? 0, right? Because I have 60 kips going to the left, I have 60 kips going to the right. There is nothing necessary to go left or right to keep this free body diagram in equilibrium. Am I correct? All right, so this is going to be 0. Okay? What about summing forces in the y direction? What would be y be?
-30, 30 down.
30 kips going down, right? So 30 kips going down. So $30 kips like that. And so we'll say that that's BY. Fair statement? And then what about moments? What's going on with moments? Well, let's see. So if I sum moments at the cut, let's just put that over here. Put that over here. So, do I need to consider the 30 kip load? No, because it vertically goes directly through B. What about this 60 kip load? 60 times 20. Then I'm going to have 60 times 10 going the other way, right? So this will be 60 times 20. Right? And so I can look at these numbers and go, I got a lot over here. I don't have a lot over here. So I need a moment over here to balance that out, right? So that means that that's the case, right? So far, so good? Okay. So make that a little smaller. So 60 times 20, that's 1,200. And that's what we're going to get. Is that fair? So this is like that. Fair statement? Okay. While we're at it, I'm just going to do something here on the board. So we'll say the rest of the member goes like that, and this is where we cut the section. And what we got was this, and we got that. Make sense? Okay. So far, so good? Okay, any questions? All right, so if you've got this, what we can do is we can construct the shear and moment diagram the same way that we would, but imagine just taking your sheet of paper and just, bless you, and just doing like that. So what we'll have is we'll have sort of guidelines that go like this. How many of you wrote here? And we're like, hey, Dr. Mike should have told me to leave some space. Gosh. So what we'll do is we'll place a shear diagram right here. And so what I'll do is I'll say V in kips. Now watch what I'm going to do with my little tick marks. Watch this. See the tick marks? See how they're pointing upwards? So it's me indicating that I'm starting at the bottom and I'm working my way upwards. So see, this whole time I've been putting those on there and it never really mattered, but here it kind of does. So it all kind of comes full circle, okay? So the way that this will work is you'll just say, okay, I'm going to start at 0, and then somebody tell me what to do. Your thumb's doing it. What were you going to say? 60 kips to the left, right? Because, see, a shear diagram, like, yeah, I mean, we're using the letter V for vertical, but really what it is a transverse force. Like, if the member's going this way, shear is perpendicular to the member, okay? So we're going to be going left 60, up, over, right? So we're going to be going like this, up, over. And I'll be honest, whether you consider that positive or negative, I don't want to say it doesn't really matter. I consider it positive because if this was a coordinate system, right, and like this was my x-axis, then my y-axis would go like that, you know, because I'm just turning the coordinate system. So I consider that positive. Okay, that's just me. I don't know that it really matters all that much. So, by the way, what would the shear diagram look like if I, instead of going bottom up, what would it look like if I went top down? Yeah, because what I would be doing is starting here, going down, over like that. It would just be flipped. It's like if you're running a software analysis and the shear diagram looks flipped than what you would expect, it's probably because you drew the member like this instead of like that. Does that make sense? So we'll get to that later. Okay, so I'm going to integrate the shear diagram. What's the area under the shear diagram right there?
600.
We'll call that positive. So we'll put our moment diagram right there. Foot kips right there. Okay. I'm going to start at 0. Okay. And so somebody tell me what to do. Tell me what to do. You're
The diagonal line up to the left.
about like that?
Yeah, 600.
To 600?
Yeah.
Okay. What happens from the middle to the top?
Nothing.
What does nothing mean?
Straight line up.
Straight vertical line up. And what happens here?
There's an extra 600 movement.
So what does that do?
It brings us back to 0.
Sudden jump back to 0 because we have that concentrated moment right here from our section cut. Does that make sense? Okay. All right. So let's take a step back. Does this make any sense? Everybody good? Any questions? Okay. So that's how you would construct the shear and moment diagram for the column. How would you do it for the beam? Well, we would do the same thing. So for the beam, what I'm going to do is I'm going to cut that section right there. Okay. And I'm going to look right here. Technically, those section cuts are in the same spot because I'm drawing the beam with some depth, but we sort of analytically treat it as just a line. So we're cutting the section right here and just looking at this. Okay. So let's see what happens there. Okay. So member BC, let's see what we've got. So member BC, I've got that. I've got a roller. The reaction on that roller was 45 kips. That's 75 kips. And then that's where we cut the section. Let's see. That's 20 feet. That's 10 feet. Okay. All right. This is point C. This is point B. Okay? So let's see what's going on. Let's do the same thing. All right, so if I sum forces in the x direction, what is Bx?
0.
If I sum forces in the y direction, what is By? 30 what?
Kips up. Down. Up.
Up, right? Okay, so By is 30 kips going up. Okay? So now let's sum moments at B. Okay? So if I sum moments at B, do I need to consider the 30 kips here?
No.
I've got 75 times 10, and I've got 45 times 30, right? So 75 times 10. So what is 75 times 10 is 750. This is what, like 1350?
Mm-hmm.
So I need more moment over here, right? I need an MB over there. So I need that. So, so we get that, right? So now let's just sort of illustrate that here on the board. So here's the member. Here's where we cut the section. Here's, the rest of the member. And what we have is what do we get? We got 30 kips upward. And we got that. Anybody notice something?
They cancel each other out.
Equal and opposite, right? Because again, regardless of which direction that you look, you'll get the same answer, equal magnitude, opposite direction. Now, here's the other thing. If you have a member, like if you have a frame that looks like this, let's say you have, something that looks like this, like something crazy, right? And you were to investigate like a given joint, right? So you say, well, cut a section, look at this member, 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 and look at all of the moments there at that joint. What will happen? As you said, they'll cancel all each other out, and they will all sum to 0 because the structure is indeed static. Well, hopefully it is. So, okay, does that make sense? And then what we can do just do what we've been doing. We'll draw our arrows. And we'll say, so what happens with the shear? Hopefully I can go through this pretty quickly because I can say, all right, we're going to start at 0, move our way up to 30, go over, go down 75, bring me back up to 0. Now, I imagine some of you who are paying attention to the areas knows that these areas aren't going to add up to 0, right? Because on the left, we're going to have 30 times 10, which is positive 300, and then 45 times 20, which is negative 900. How are we going to get to 0?
Sudden jump.
A sudden jump of, and I didn't write it up here, but now I will, 600 foot kips right there. So what does our moment diagram look like? Well, let's see. Let me draw these guidelines down a little bit. Start at 0, sudden jump upward to 600, then a linear increase to 900, and a linear decrease back to 0. Does that make sense? Okay. All right. How are we doing so far? Any questions? All right, I'll leave this up here for a sec because I know some folks are still writing stuff down. All right. Sound good? Okay. I want to go back to the presentation a bit because I want to talk about this analysis aids topic here. Okay? All right. Everybody with me? Okay. I want to take a look at this slide. This slide includes some really challenging beams. And we've done stuff like this in here. Okay? We've looked at problems like this. Problems that are of this complexity. And I don't shy away from it, nor do I think it was a bad idea, because I'm of the opinion that if you can analyze something like this, you can analyze anything, right? But the truth is, you won't find any of these beams in this building or in a bridge out in the real world. This is complicated, and if I'm being honest, this is way outside what you would find in most real-world applications. In most real-world applications, you're going to find something like this, just a simple cantilever beam. Now, I put this on the slide to sort of explain routine bread and butter structural analyses that engineers are doing all day, every day. So I want to talk about these two beams, okay? And my question to you is there really, really any difference between these two beams? No, there really isn't. The only difference is the numerical inputs, right? So we have here a cantilevered beam with a distributed load. Here we have a cantilevered beam with a distributed load. Now, I am not one to start throwing alphabet soup at problems unless it's absolutely necessary. But I guess my question is, instead of treating this and this as a separate structure, what if I treated this as W and treated the beam length as L and developed a formula for what is the reaction, what is the maximum shear, what is the maximum moment, and treat the problem symbolically, okay? The beauty of that is I could develop a simple plug and chug expression that would get me the answer for any cantilever beam subjected to any distributed load. Does that make sense? Okay, that is the nature of an analysis aid, okay? So let me show you what analysis aids look like. I'll just, give you an example here. So, I hope I don't mess anything up here. Let's do AWC. AWC shear moment deflection. Okay, so this is from the American Wood Council, like wooden structures and timber structures, and this is a design aid that anybody can download right now. These are shear and moment formulas for. Oh, I scrolled a little bit. If it'll decide to load, for various loading conditions that I would call typical loading conditions. Okay, so for example, if you look here in the table of contents, we have simply supported beams, we have concentrated loads at the centers, we have cantilever beams. Let's look at, for example, figure 12 on page 9. We're going to derive this here in a second. So here's a cantilevered beam with a uniformly distributed load, and we're not going to worry about the deflections for today because we can look at that later. But here we have a cantilevered beam with a uniformly distributed load. Here is the load. Here's what the reaction is. Here's the shear as a function of x. Here's the moment as a function of x. Here's the maximum moment, maximum shear. Plug and chug, done, right? And for simple, straightforward loading situations, these are very valuable. If this is going to be your bread and butter analysis, there's really no point in taking the time and constructing a shear and moment diagram if you know what the answer is every time. Does that make sense? There's really no point. Just use one of these. And engineers will use these quite often, okay? And a lot of times structural analysis professors won't even talk about this. They'll treat it like it's some hidden, guarded secret. But come on, they're out there, so let's just embrace it. There's a couple things that I think you need to be aware of. The first thing that you need to be aware of is you need to be very careful in terms of what the formula is asking for. So, for example, let's take this problem here. So I have a beam with a triangular load on it. Okay, now this is from the steel manual. Okay. This is from the steel manual, and it will tell you, here's the shear as a function of x, here's the reactions, here's the maximum moment, even where it is, maximum deflection, all of that. And in the formula, you see this term W. Like, you see this term W's everywhere. W, in this case, is not this, okay? W, in this case, is the total magnitude of load. So if you plug in 2.5 kips per foot into these formulas, you will get the wrong answer. W in this case is the total amount of load, or 50 kips. Okay, so you got to be kind of careful when you use them. Okay, I'm not saying they're not valuable. Don't start plugging stuff in because the math won't work right. Like for example, if you look at the values for shear, like the reaction here, like here's the shear diagram. The reaction here is W over 3. Well, if you take this and divide it by 3, you'll get kips per foot. You won't get a shear in kips. So the units don't make sense. Okay? Everybody with me on that? Okay, here's another one. Let's take a look. Oh, my animations, I need to fix that. Let's just take a look at this. Okay, so here's a common loading scenario that you would find in the real world. Okay, so this is a simply supported beam that has a uniformly distributed load and it has a point load, but the point load is not in the middle. Okay, so I don't have an analysis aid for this situation, but I do have an analysis aid for this situation and this situation separately. Just add them together, but you need to be very careful about that. When you look up the answer for this analysis situation, it'll tell you M max. M max is WL squared over 8, and that occurs at midspan, like in the middle of the beam. M max over here does not occur in the middle of the beam. Like think about what the shear diagram looks like. Think about what the moment diagram looks like. The maximum moment is going to occur here, right? So if you just take this maximum moment and add it up to this maximum moment, you are not going to get the right answer because those are at different spots. So if you wanted to figure out like the maximum moment on this beam, instead what I would do is I would do one of two things. One is instead of using the maximum moment formulas, use the moment as a function of x formulas, like plot them, and just use Excel to figure out the maximum moment. Or you could add the two formulas up, take the derivative, set it equal to 0, solve for x, take that value of x, plug it into the function, get the maximum moment that way. That'll work too, okay? But you can't just take this number and add it to this one because they are at different places along the beam. Moment is a function of x, and the x value for these two formulas are different. Okay? Does that make sense? So you just got to be careful with it. Okay? All right. Make sense? All right. So I want to derive some of these formulas for a simple case because I want you to have some background as to where these things come from. Okay? So I want to look at the following expression. I want to derive the following, or the formulas here for this problem. Okay? And so I do want to get symbolic. Again, I don't like throwing alphabet soup at a problem if it's not necessary, but I think now we can respect that there's a reason for it, okay? That it will lead to an analysis aid that we can use over and over again, okay? So I want to treat this problem like I would any problem in this class, okay? So how would you construct the shear and moment diagram for a cantilevered beam? Ignore the symbols. Like, if I wanted to draw the shear and moment diagram for this beam, what do I need? What do I do? What's the first thing to do? Reactions, right? So we need reactions, okay? So we're going to have, let's see. So we're going to have a reaction here, right? We'll call this a vertical reaction, right? And we're going to have a moment reaction, which I'll call Rm. Symbols don't matter, just something. Okay? What would we have done if these were numbers? Tell me what, I mean, before we start writing equations, there's something we would have done. What would we have done with that distributed load? Collapse it into a point load. Okay? So we would put a point load, something about like that. What is the magnitude of that point load?
W times L.
W times L, right? So we would put WL. Okay? Where would we locate that?
L over 2.
L over 2. So we're not thinking in terms of numbers now, we're thinking in terms of symbols. Okay? But again, we're trying to get to an analysis aid that we could use over and over again. All right? So tell me what to do. Okay, some forces in the y direction. And just so you're aware, I'm going to draw the diagrams under the beam, so as you're writing this on your notebooks. So, what forces do I have going down?
WL.
WL. What forces do I have going up?
RV.
Right? So, up here, RV equals WL going up. Okay. Now tell me what to do.
Sum the moments.
Sum the moments where?
About
The support?
the support, yeah.
Okay, so let's do that. So here I'm gonna, if it's okay, I'm gonna scooch this just a little bit over there. All right. If I'm summing moments at the support, do I need to consider RV?
No.
What about RM?
Yes.
Which side of the table?
Left.
left, it goes left, and what's the distance? Is there a moment arm?
No.
It's just RM.
And what resists it? What goes the other way?
WL times L over 2.
WL times L over 2, right? So So what does RM equal? WL squared over 2. Like that, right? Does that make sense?
Isn't it the other way? Shouldn't it be rotating the other way?
I wrote it right here wrong there. Yeah. This one's wrong.
Yeah.
But the one up top, that one's right.
Right, yeah.
Yeah, that one's right. I think I had this in my head, like they were going the wrong way. Okay. So, let's continue the exercise. Okay? Okay. Let's draw the shear diagram. And notice I'm not putting any units here because this is all symbolic. There are, I'm not really thinking about units. Okay? So I start at 0. Tell me what to do. What do I do? I start at 0. What happens from here to here?
You had that the WL load,
Oh,
like the whole thing.
so what do I do that? No.
It's a diagonal line.
So it's a line like that, and I go down to WL, right? So I go down to WL minus WL, and then I've got that reaction, brings me back to 0, right? Okay, so how do I construct the moment diagram? How do I do it in any time? If I have a shear diagram and I want a moment diagram, what do I do with it?
The area under the curve.
I integrate it. There we go. What is the area of this triangle? Let's reason this through in our heads, okay? What is the area? So it's going to be negative 1/2. What's the base of this triangle? L. And the height is going to be, WL, right? So that is what? WL, or negative WL squared over 2, right? So if I start at 0, what does my moment diagram look like from left to right? What is it? Linear, straight? What's it look like?
Parabola.
Parabola, right? Okay, so is it going to go up or down?
Down.
Down. Is it going to go like that? No, it's going to go like that, right? Little to a lot. Little to a lot. And what does it go to?
Negative WL squared over 2.
And what happens here?
The reaction moment brings it back to 0.
A sudden jump upwards. Is it really that scary because it's symbolic? Hopefully not. Okay? Now, that doesn't help us. Well, I mean, it does help us a little bit. We still got a couple things we got to figure out. I'm going to knock one of these out real quick. So what about Vmax and Mmax? Well, whenever we write these out, we typically write them out as absolute values for the purposes of a formula. So Vmax is just going to be WL. That's going to be WL squared over 2. And I'm coming up with this because this is the absolute biggest value that I find on either diagram. The absolute biggest one. But how do I get the functions? Well, the way that I get the functions is I cut a section. Okay? And I cut a section some distance x away, right? So like if this is the origin, right, that's the x-axis, that's the y-axis. Maybe I'll do that. Maybe I'll say, that's the x-axis, and that's the y-axis, so we're some distance x away from the origin, right? So I'm going to cut a section. Which way do you think is easier to look? Left. Okay. So all right. Okay. Unknown shear, unknown moment, right? This is W, this X. So what do? Take that distributed load, collapse it into a point load. How much is the point load?
WX.
WX times a moment arm of, and it's the same story, right? So I sum forces in the y direction. Do I have any upward forces? But I have a WX going down and a V going down. Right? What about summing moments at the cut? Hopefully I'm not going too fast on this. If I am, tell me if you're wondering where this stuff's coming from. But hopefully this should be pretty simple. Right? So I've got WX times X over 2. And then an M also going the other way. Notice anything about the red and the blue boxes? What's that? What is the derivative of that? It's that, right? So if we go up here, we can say my pen's getting minus WX minus W over 2x squared. What do you think? It's not too bad, right? Pretty simple. And by the way, look at what we've got here. So the reaction, which is the maximum shear WL, WX. So it doesn't put the negative because it shows the picture and shows it's going down. WL squared over 2, WX squared over 2. The one thing we haven't discussed yet is the deflections, and we can talk about that later. So we haven't even talked about beam deflections at all, so but we'll get to that. What do you think? All right, the only other thing I wanted to mention before I let you go is that I've got 2 problems on the next assignment, so I made it worth a little more. So it's worth 15 points instead of 10 because I wanted one of these. But it shouldn't be any harder. So. And it's not due till next Wednesday. Sound good? Well, enjoy 5 days away from me. I will see you all on Monday. So.